Hello, and thank you for joining today for this educational Innovize webinar. My name is Caitlin Nine, and I'm part of the marketing team at the Innovize Portland office. During today's webinar, you'll learn how to find the right fit for you and your team. Every stormwater engineer has a different approach when it comes to designing stormwater networks. That's why XPDRAINAGE focuses on streamlining your sizing options. We'll give you more control of what to adjust. For those of you who may not be familiar with Innovize, we have a long history of providing high-performing, innovative, and software solutions. Our intention is to make sure that in our work, you can design, model, review, and manage with confidence. This also means that we strive to provide excellent customer service and support, and that we continue to offer continuing education opportunities like these for engineers and others in the industry. Innovize offers a library of software programs for design, analysis, and management of water infrastructure, including powerful storm and flood modeling software like XPDRAINAGE, which you will see today. Now, on with our presentation. I'd like to introduce our presenter. Today's presenter is Zach Sample, our Stormwater Products Manager. He has over 10 years of civil engineering experience in site design and stormwater planning and hydraulic analysis. Zach has performed a number of advanced water resource studies, including hydraulic and water quality system assessments, as well as 1D and 2D hydraulic river and flood plan studies. During his time with XP Solutions and Innovize, Zach has helped hundreds of clients with their models, conducted training courses, and led the development of our stormwater design software, XPDRAINAGE. Thank you again for joining us. Would you like to start a discussion, Zach?
Yeah, thanks, Caitlin, and thanks everyone for joining today. Again, my name is Zach Sample. Let's dive right into what we'll be talking about. So the agenda today is really, I guess, to start us off with really what are we trying to do in terms of stormwater design. And I'll kind of frame that to some of the workflows and practices that the industry-wide we currently do, and something that we've been working on and collaborating with engineers to try to streamline and really just make easier. And ultimately we'll dive into looking kind of in a live example and working around and kind of seeing for ourselves if those workflow improvements kind of really do stick and really do help. So the first piece is just really what are we trying to accomplish? I like to start these presentations with really giving us a kind of a general starting point. So the idea of all civil engineers, especially all water resources engineers, the idea of this safely and responsibly developing and modifying infrastructure. That's what we're all trying to do, right? So starting with just that everyone, whether you are a consultant or you are some review authority working for a municipality, everyone is trying to do the same thing, right? Safely and responsibly change the world around us. So when we start talking specifically about stormwater and stormwater design, practically speaking, I would say that every municipal guideline and consulting practice is unique. So you might work maybe there's one county next to another, perhaps their guidelines are almost identical or quite similar. I'd say largely even between different counties, even different engineering firms in the same municipality, the same city area. There are differences. There are sometimes quite stark differences in guidelines and really how we're all encouraged to safely and responsibly do this work. So simply put, everyone does things a little differently and everyone's asked to do things a little differently. Ultimately, when we come to stormwater design, we're trying to do a handful of things. We're trying to assess these. So the first would be to look at an underground network and ensure that it will safely accommodate usually more minor events. I'd say maybe the 5 or 10-year rainfall storms. Sometimes that can be a lot higher. Maybe even the 100-year needs to be safely accommodated underground. So that's one of the first things we're going to look at. The next, and this is really kind of pervasive throughout the US, but it's to consciously keep in check the water quality runoff from our sites. So reduce or eliminate water quality runoff. Another piece. Next is everyone generally tries to follow some version of this, basically a kind of no worse than before major event mitigation, right? We're going to have this perhaps catastrophic flood, this 100-year or greater flood, if we're developing some form of development, some land area, we're probably going to pave it, change around the hydrology. Okay, we need to make sure that we aren't making it worse than it was before we got there. The last piece would be that we need to have, we need to lay out buildable, effective management systems. And this is really kind of a broad topic here, but we need to have designs. If we're stormwater designers, if we're water resources engineers, we need to really put forward designs and plans that can be built, right? That can be built and can be maintained, kind of once it leaves our hands. Those are clumps of tasks that really everyone in one way or another has to accommodate. And one thing that I've presented on a number of times, I've spoken about quite a bit at shows around the US, is really on a number of these topics. The water quality runoff reduction in particular, yeah, that's a really in vogue. Last 10 years, we've really, as an industry, come to start implementing this, and it's required to reduce water quality. One topic which really hasn't been discussed as much, and what I found by discussing with engineers and partnering with engineers over the last, I guess, the end of 2017 when we worked on XPDRAINAGE, it's the underground network, the pipe network. There are so many different ways that people try to come up with a design. So that is really what we'll talk about today, is specifically this topic, which I don't think really gets a lot of discussion. And something that we have really worked hard to make, frankly, just a lot easier to accommodate amongst the rest of these items. So next, we'll look at the workflow and really what we're trying to do when we're designing and sizing a pipe network. So you'll see I titled this workflow Preliminary Sizing and Full Analysis. So there's a bit of a split here. So in many cases, I'd say the industry might even be split 50-50, depending on what project someone's working on, or perhaps just the different engineering firms. There is a general workflow around a more static, a more preliminary, rational method sizing. That's what I see here, these design flows. So either starting with basically a rational method, so it's just a flow, right? There's no time involved. There's no time step, no hydrograph. It's just flow, Q. Q equals CIA. So you either have that, which is basically a hand calculation, or perhaps a more, I guess, rigorous full hydrograph solution, full hydrograph inflow into a model. And that is really kind of where this split occurs. I mentioned a couple examples, SCS, Santa Barbara urban hydrograph method. There's a number of full hydrograph procedures. But is the inflow that is really the kind of main design constraint for a network sizing, is that static, is that rational, or is that a full hydrograph? That's where the split really begins. From there, well, there's a whole range of criteria that engineers use on a regular basis. So depending on your site, depending on where you are in the country, there are a range of different items like, all right, sizing, or I guess setting the elevations for a pipe network to accommodate a minimum velocity, let's say, to ensure that, right, dirt and debris is kind of scoured out, the system doesn't fill up. Maybe min-max slope, a certain cover level, a whole range of different design criteria, I might call it, that maybe no one person uses at all, but everyone seems to need different pieces. Again, I'm trying to really frame up where we're at the moment. Okay, so the next would be, well, we have these inflows, either they're static, as I'd call it, that rational method, or a full hydrograph method. Well, we get into a hydraulic assessment. Okay, are we going to maybe just use the Manning's equation, a static Manning's equation, basically something we could do by hand or in a spreadsheet to give us what the pipe full flow capacity is. Okay, that's that static side of this conversation. The full dynamic hydraulic analysis is kind of the other extreme. Is perhaps I might refer to that more as the realistic. Again, it's a little made-up answer, but it's really accommodating a full hydrograph in a complex, I guess, site where you're going to have the timing and the attenuation through facilities is going to be probably completely different than a kind of static assessment would show. From here, I guess, what else are we trying to look at? There's surcharge pipes, manholes, flow capacity comparisons. That might be something on maybe more the dynamic analysis side. Maybe I just need to ensure that I don't kind of pop the top on some inlet grate, right? I don't allow flow to spill out onto my street. Maybe that's a design criteria. So looking at this list, you can see that there's a pretty high number of possible combinations that people might readily use. And so everyone's a little different, and every municipality might look for different things. So that's kind of where we are as an industry at the moment. So I have a poll. I'm always really curious to hear, I guess, who has joined the webinar, what they think. So I'm going to launch a poll, and you can interact with this and click. Basically, it's how do you size pipe networks? I guess, all the way at the bottom of the list, you really kind of do a combination of everything you've just seen, or perhaps maybe second from the bottom, that you don't usually size pipes on your kind of projects. Okay. At the top, that preliminary sizing, this is really a comment I refer to as kind of a hand calculation, right? So the rational method, Manning's, it's not very rigorous to solve, okay? So that might be if you're used to using Excel, used to using some simple hydrology tools, that's probably more that preliminary sizing approach. The term preliminary sizing, that's what the Federal Highway Manual refers to it as. So there's also this, basically, start with preliminary sizing. Maybe you're done there. Just go into dynamic sizing, like a full hydraulic analysis to see what happens. Use a combination of both, right? Looks like most people have entered in. All right, I'll close this and I'll share this with everybody. Pretty interesting numbers here. So let's share. And you can see here that, it looks like most people, I guess if we add them up, well, 35% say they use a combination of all these practices. That's pretty common. I guess my personal consulting experience and the groups that I've directly worked with, there's not every single project is exactly the same. So yeah, I'd expect there to be kind of a combination of, different jurisdictions you're working in, different projects. But you see that there's either start with preliminary sizing and then perform a more rigorous analysis. That's that kind of 32%, or, a little over 40% say, just that preliminary, that rational method pipe sizing is how they assess pipes. Okay. So it's very interesting. And this isn't saying that that's all that's done. Most engineers might size pipes that way, but then really still use a full analysis, elsewhere to look at your 100-year kind of no worse off condition. So thanks. That's really interesting to see. So now let's dive in to what we've really worked in XPDRAINAGE to accommodate all these possible choices. Okay, so the idea that's pervasive throughout XPDRAINAGE as a tool, and what we've worked with engineers and what has a lot of groups have found really valuable, is that you can kind of jump in or jump out wherever you need. So you don't have to do every single checkbox. You don't need to run every single design analysis. What do you need? Get in and use it, and then push it all back out to CAD or GIS. That's really the way XPDRAINAGE works. So we're going to start by, all right, well, we could absolutely have the static, as I'm calling it, rational inflow. Static is just a way to define whether it's a hydrograph or not. So all right, you can in XPDRAINAGE really directly start using and assess what the rational method flows will produce. Well, from there, you can also then size a pipe network and modify a pipe network based off of those direct flows, those Q values. And there's also something we've talked about quite a bit in other webinars, is the whole range of design, kind of smart design starting points. That's kind of how I refer to it, but really a smart guess, a smart first go for your stormwater controls. Stormwater controls being your ponds, your swales, your pervious pavement. All right, so it's kind of more on the preliminary side, right? But we can get a really smart first answer to go with, and really then running a full analysis might be a way that would change, but we can get that first really good starting point for ponds and outlets. So that's all in the preliminary sizing world. From here, we could then also go right into also assessing a full hydrograph, right? Let's say someone's using the SCS runoff method. Okay? Well, we can directly do that as well. That might morph into, well, if I've already given initial sizes for my stormwater system, well, now I have a full hydrograph inflow. Well, let me run a real dynamic hydraulic assessment. And that, kind of the true system performance, okay, as opposed to the static, the full hydrograph, dynamic hydraulics. Of course, it's still a computation. It's not, a real storm or a real answer. But it's kind of that more true realistic representation. That is ultimately the last piece we really need to maybe fine tune our model to submit and to report what we have. So yes, absolutely. All of these pieces that we have talked about, we can do. Now, and actually I'll walk through this in a little bit in the software. Practically speaking though, not everyone, judging by the poll, not everyone might want or need to jump through each and every one of these steps. So what do? So in XPDRAINAGE, we can do all of this in one place. And that's really quite useful. And that has been really, really useful and efficient for a lot of engineers. But okay, what if we only need to have some sort of, I don't know, schematic design, right? Maybe you have a lunch break and someone walks in and says, hey, I need to know what this site's going to do so I can bid on it. Let's just say. Maybe you're only going to want to do a preliminary, as I might call it, sizing. And that's really common. The idea here is we don't need to be sitting in 3 or 4 or 5 different spreadsheets to have this answer. It's very direct and very straightforward to do in XPDRAINAGE. Okay, and again, I call out spreadsheets because I used to do that quite a bit. So I'm pointing a finger at myself of how I used to work. So we can directly look at preliminary sizing and size the network in just a matter of moments, matter of clicks, and that can be ultimately what we submit. Maybe that's as far as the project you need to take. Though in your next project you get, maybe you need to do something different. Maybe you need to have the smart starting point for your ponds and your outlets, but you really need to or want to run right with a kind of a dynamic full hydraulic system. Maybe that's something that you would like to do. Maybe it's, you kind of get the idea here, right? But maybe it's you start with a good static inflow, you size your pipe network, then you run a full analysis. So all of these different combinations, you have the control to use or to not use. Okay, that's the point of XPDRAINAGE. Okay, it's a tool in the toolbox. If it makes things more reliable and more efficient, well, then it's useful. Okay, so that's really what I'm trying to call out here, is that all of this is in one. People have found it to be quite logical, so it's in a kind of one logical space, but you don't have to do all, let's say, 6 steps. If you have a project that only needs preliminary sizing, great, we can do that, and that's really what this latest release accommodates. So I'll just take a couple quick kind of snapshots of how we do this. So it's great to talk about it. Well, there's that preliminary inflow and that dynamic inflow, as I refer to it. The rational method, I'm sure everyone is probably quite familiar, but flow, Q equals CIA. That's the basically the calculation. Well, here is the input. So I would need an area, that volumetric runoff coefficient, and a time of concentration. Okay, great. Of course, the intensity comes from our IDF table we'll look at later. So we also have perhaps a full hydrograph method. Well, you can imagine here, this is all in one place. So what does this mean? This is a little different. This is in fact quite unique. So all of this assessment is done in one tool in one place. So how do we do that? So you can see the laser pointer here. You can choose to fill out whatever section you'd like. So typically, you might only use the dynamic, right? That full hydrograph method, and you can leave this blank. You don't have to fill out the preliminary sizing. That's only for specifically the rational method for, let's say, the sizing the pipes. We'll look at how this works, how this comes together. You'll see let's say if we were to edit the time of concentration for our dynamic section, well, it updates the preliminary sizing. So you only really got to enter information once. But this is combined. So we don't need to enter in the preliminary sizing if all we're doing is dynamic. But from that poll, it looks like 90% of people who are attending this have all said that they either start with preliminary sizing and move to dynamic, or just use dynamic, or just use the preliminary sizing, or bounce in between the different approaches between projects. So what we've found so far is that this option has really been quite nice for engineers to have access to. So the next piece, all right, so we have our inflows, whether it's preliminary, whether it's that full hydrograph. What do we want to do? So how do we size a pipe network? Well, we have a pretty logical ribbon. You kind of walk through our ribbon and you finish your project, right? So import, maybe look at some rainfall, preliminary sizing. So in this case, you could go to our pipe sizing wizard, which would be, of course, for the pipe network. There's also these calculators for water quality runoff reduction, for that smart pond sizing, so on and so forth. So if we were to pick the pipe sizing wizard, we'll look at this live in a moment, but we'll see we can have a whole complex pipe network that we simply say, yes, we want to size that network and all of its connected tributaries. And all the criteria I mentioned before is all kind of in this one dialog. So you can pick your IDF table, pick your rainfall event. Let's say I have the 10-year design storm is what I need to assess with my pipe network. We'll see that we could have I guess here's a snapshot of the Atlas 14 IDF table. Great, you can import that given your area. We also have a default pipe size, min, max, slope. All of this, of course, is customizable. If you have something for your area or you have a different list, I used to work on projects where you started with an 18-inch pipe. That's it. You start with an 18-inch pipe. And if you need to go larger than that, you go up a very large difference in size. So this all can be customized and saved as a template for use. But of course, by default, there is a list. And we get into, actually, I'll step back one. We'll see on this screen here, on this right side of the dialog, we have all the different knobs to turn. So we can have our design level be the top of pipe, the obvert, or the invert. We could have a cover depth that's required. We could have min-max slope or velocity. Any combination of these design criteria, you could spend weeks playing around with some of this if you wanted to fiddle with a model. But it's as easy as pick what design criteria you care about and go. So you hit next. And here we're going to list, all right, well, based on what you have said, in yellow is a difference. This pipe used to be 12 inches. Now it's 18. It got increased in size. The last piece, again, if everyone, let's say, tries to assess a pipe network or a site differently, you can imagine that everyone tries to or wants to report differently. So we have a range of different reports and a lot of output. You see here we have kind of a full report, this HEC 22, that's kind of Federal Highway Manual. Literally, it's the preliminary sizing output table as listed in the Federal Highway Manual. You can pick what source you want. You could save it, work with that directly, maybe use some of the information. But really, any different way that you would care to see these preliminary sizing results, they're all here. And from here, okay, well, I have my initial size of my network. Now I maybe want to have a full, maybe rigorous dynamic hydraulic assessment. You see here, well, in this case, we would use a profile is one way to really easily understand what's happening. In XPDRAINAGE, we're trying to make it hard to make a mistake. That's the intent, right? So I see this profile, and right away I see there's a couple odd items. There's this little orange chevron, this little icon here. So, well, at this point, it looks like I'm flooding. So I'm surcharging this manhole. I guess I'm surcharging the pipes, I should say. So this is orange saying, oh, well, maybe you don't want these pipes to be overtopping. At this point in our network, there's not a manhole here, but you can see that these pipes are surcharging. There's more water trying to be pushed through them, right? Then there's direct capacity. Those are a couple things that we're going to see in a dynamic assessment that we aren't really going to understand in a preliminary sizing approach. Obviously, with a full hydraulic assessment, we're going to get the graphs. We're going to get information that otherwise we wouldn't. So if we were to, let's say, just jump into a dynamic assessment, a full hydraulic assessment, and we didn't look at preliminary sizing, well, we're going to make that easy to use as well, right? So in that case, for the full hydraulic assessment, we're going to call out where we think there might be an issue. So this flow capacity. So the flow we're calculating in that section of pipe, how does that compare to the basic Manning equation, pipe full flow capacity? So it's kind of the real answer versus, the static capacity answer. And if that's 0.8 or if that's over 1 especially, that might not be something we want to have happen. So if I was to, as we'll see in the model in a moment, if I was to just run this assessment and look at just the dynamic results without doing any initial sizing, well, I could just go and change just these two undersized flat pipes and be done. So I would probably have a little, I guess, a smaller pipe network, probably more cost efficient by just directly doing a dynamic assessment. But we'll see that in a moment. We'll see also, I mentioned that there's that table that had those red, hey, this might be a problem. Well, we're also going to show this in plan view. So hey, I'm looking at my model, and you know what? You kind of can't miss that there's a couple sticks of pipe that are a different color. Hey, these perhaps are undersized, is what this is saying. So you can investigate. Maybe this is fine, but in this case, this is a roof lateral coming off a building, probably very small, maybe needs to be upsized slightly. So again, whether you jump in and do preliminary sizing, and that's it, or you jump in and do just dynamic sizing, dynamic assessment, either way you do it, you're going to easily see the results, get the results, understand what's happening. So this can all be done fluidly together. The last, actually this little video, something you'll see me play with in a second, but we've added more than just, I guess, the pipe network sizing and configuration. We've added in this latest release, there's chambers. So many of you are probably familiar with this, the idea of underground detention chambers. I'm in this case showing an arch chamber facility. These are really common, and something across XPDRAINAGE is the idea that it's really this seamless, true to built layout of a system. So I'll even play that video again now that we're all watching it. So the actual numbers that are going to be used in this calculation, Those are always updated and shown against the plan. And you'll see as I moved the layout around, well, the dimensions and the layout of that facility also got updated on the fly. So if you have a site, you can enter in values to start. You can drag and move and put your facility where you think it's going to go, based on a CAD file or an image. Use some sort of one of the many calculators to give it a good starting size. Any way you do it will always represent these facilities on the screen. And chambers are pretty funny little structures, right? They're not like a pond or a swale. They're these little compartments, right? So as you'll see when I'll play it one more time, when we move the layout, you'll see that it only snaps to the complete sections of pipe, right? We couldn't order 3/4 of a length of one of these chamber sections, right? So in plan view, the software is going to help you set out the layout with whatever buffers, whatever overfill you're going to have. So that's a pretty useful one that is in this release that we've worked quite a bit on to make it as seamless as the rest of everything else that everyone has come to know in our software. So let's just jump in and play around with the things that we've just been talking about. All right, so here's XPDRAINAGE. And here, kind of from the top, is that ribbon I was referring to, right? If we were to work across left to right, well, you kind of finish your project, right? You can import, set out some preliminary sizing. It's useful. Hey, if you have information somewhere, maybe this was already done. Maybe you already have catchment layouts in CAD or GIS. Excellent. Import that as easy as, select import or right click on a layer and import. Okay, bring in your pipe network. In this case, I have 2 different phases that I'm playing with where I have imported a pipe network. And just for the sake of time, I just kind of jump right into what this looks like. So here I have, we'll see if we can zoom in. We have this pipe network. It's pretty small in size. So we can see here a 4-inch diameter roof lateral. So you see this magenta line. So pretty common. You have a small roof lateral coming off. Pipes get larger as they go downstream, which is a good sign. Here is the chambers that I was playing with before. So let's take a look at kind of what we can do with this. So talking specifically about the inflows to start. It's a pretty big change for people. There's really no software that I'm aware of that sets it up like this for us. So knowing that we all really do work one way or another around this topic of probably having some sort of rational method, preliminary sizing, and dynamic full hydrograph hydraulics on any given project. You can choose to use one or the other. In this case, right, we have both. So I had saved this as a template. And we have, just like many of you might have already seen or used this in the software, we have calculators, right? I could use a calculator to set out from a list, in this case, the SCS method, pervious curve number calculator, great. Well, same ideas exist we have calculators to calculate runoff coefficients, time of concentration, so on and so forth. The idea here is that anything in red, I have manually typed in. So some of this was just, I saved this info as a template, and when I import objects, I can just pick, hey, here is my commercial land use template. Well, I went ahead and entered in 0.8 as my rational method C value. So great. So we have both of those preliminary sizing and full hydrograph at each of these inflow areas. So from that, I guess what can we do? We could look at our flow path. So I could right click and go to pipe sizing. I could also, under preliminary sizing, go to this pipe sizing wizard. So let's just take a look at what we have here. In this case, we have, I'll show the whole pipe network. You'll see it is going to show it's going to show that entire flow path and all of the connecting pipes, all the tributaries off of that. And you'll see I have all these, red, very precise values. This was imported directly from CAD, right? So something in red was kind of manually input. Well, I imported that network from CAD, and these are the values that were in CAD. Great. So next, we could look at the different input. So I happen to have an IDF table here. I could take a look at that. Here is, from Atlas 14, this huge ranging IDF table. From this list, I could pick what storm. I want the 10-year event. Great. Here is the, in this case, the default US, probably pretty common pipe library. Min, max, slope, all of this could be adjusted, or again, kind of ignored if you just want to have just a couple pipe sizes in here. But great. So we have our IDF table, our pipe network, or our pipe library. And we get into, on this right side, all the different knobs we can turn, right? So since, let's just say, I have a project in this very specific example of someone has already laid out this pipe network, and I'm really just gonna check that system in XPDRAINAGE. Okay, that's quite a laborious path to take. Probably takes a lot longer to manually enter in and set information in Civil 3D than you can automatically apply all that in XPDRAINAGE. But if I have information, if I have inverts, maybe I'll just lock slopes and inverts of these pipes. So all I'm going to do is change the diameter. That's all I'm going to do. So I can hit next, and we'll see that sure enough, it increased the pipe diameters, right, where that flow needed to. So you see it used to be 4 inches, now it's 6, so on and so forth. Okay, so when I finish, it always pops up one of these preliminary sizing reports. So this is kind of the default. This tells us a lot of information, total contributing area, the rainfall intensity, ultimately the pipe velocity and flow. Okay, I could switch this. I could look at a full report, the HEC22 report, if anyone uses this directly. I think actually a lot of people do. But this is verbatim the exact format used in the Federal Highway Manual. Length and contributing drainage area and upstream inverts, downstream inverts, ultimately the flow and velocity. So all this information is here. But what just happened? If I wasn't talking so much, what just happened? So it just took a moment. Basically, it was just a couple clicks, and I picked my design criteria. We can now look at this network. I'll turn off that bottom display. Now, I assume everyone had perfectly memorized, right, what the pipe network looked like before, but I can actually just jump back in time, hit the back button. That's pretty useful, actually, right, to make a change. What was it before? So you can see much smaller pipe network, okay? Probably a lot cheaper to put in the ground and to buy. Well, hey, you know what? Based on our probably pretty conservative, rational inflows, hey, we have to bump all of these sticks of pipe up. There you go. That's what a preliminary sizing would give us. Well, let's not stop there, right? So we could report, we could use this. I could also jump right into, let's have that network, but let's assess it with a full, like, hydraulic assessment. That's what this analyze go gives us. And this is running actually 3 different phases, basically 3 different design ideas, and a range of rainfall events. So we'll see what we have here. First thing we're going to look at, in this case, I want to look at that profile again. And I'll switch to the worst event, the 100-year rainfall event. So in the worst case scenario, I can play this animation over time. We'll see this fill up. right? This system fills up. This is a detention facility, and there's an outlet here that's blocking the flow, which is what we want. But you'll see this pipe network is really not full. Okay, so something we'll probably find a lot. Preliminary sizing is going to give us probably an overly conservative, right? Too large of pipes. Great, so even in the worst case scenario, we can zoom in here. We can see that this is not full. So another way to look at that, I could go into results and I could look at the connections summary. Show me the worst storm event, critical storm. We'll see that the flow capacity, very, very, very small relationships. So probably not an optimal design. We could jump to basically a duplicate of where we started. So I'll show provide. And you see this was our initial, right, very small network. Well, you'll see that these first couple pipes, these little 4-inch laterals, they're underwater, right? They're kind of, the HGL is shown to be above the top of pipe, means that we're trying to get a lot of water in here. And at this location, we can see that there's, icon showing warning, we're getting above the top of this pipe. So what's happening here? This is the dynamic full hydraulic assessment. Well, in this case, we're seeing that there's a couple, perhaps, items we want to tweak. Here is that connection summary. And it's identifying these two pipes, right? So I could go in and I could edit these two pipes. All right, so pipe 2 was, in this case, 6 inches. I can make that 12. I can make that, I'll bump that up maybe 12 inches. Pipe 8 was our other one, very small. I'll make that, I guess, 6 inches. So I could just change these two. And let's run the analysis again. Let's just see what happens. This would be maybe the approach of if you had something laid out and you just directly want to go into a dynamic, more realistic answer. Perhaps also a more cost-efficient answer. So let's look at these results again. This first pop-up is for our stormwater control, our summary there. I just want to first go and look at our profile. And we'll see that if I have changed this, right, our first pipe, we've upsized a little bit. Well, you know what? We didn't upsize the second one. Now this one will probably be surcharged. We could change that with just a couple tweaks in our design. In this case, this is okay because it's really dependent on this underground facility, right? So this is causing a backup at this pipe location. So it's not the pipe's undersized, it's that our detention facility is too big. Or sorry, our detention facility is detaining flow. So this probably going to give us a more cost-effective design as opposed to that other option where we just started with the rational method. Okay, that'd be a little oversized, but you get the idea. So that's really the different combination of the pipe sizing approaches. That, as I mentioned before, there's kind of 6 different pieces that you can absolutely move through it all together, or just do preliminary sizing, just do the full dynamic hydraulics. We can play with this arch chamber for a bit here. So this is, again, as I showed in that video, many of you are probably already familiar with kind of how XPDRAINAGE works, right? But if you have a pond or some sort of facility, any of the input here is going to always be reflected out in the plan view. And I can change see, this is in section. We can see there's this embedded, there's fill above, perhaps fill below. We're going to take that into account, right? The storage within that media. Here's maybe a better image of what these arch chambers are. We have a range of different facilities. So arch is probably one of the most common. And you see that any change I make, if I was to change from the plan view out here. Great, maybe I could go in and start changing values. All right, we'll see if I start trying to modify numbers, it's going to give us a best fit. All right, undo that. Maybe I want it just to be a lot longer. So it's very, very quick and easy to get an understanding of how many of these chambers, how this will lay out on our site and how this will work. So as soon as we use, like in this case, the sizing calculator for a preliminary sizing, or run a full assessment and see if it works or not, any tweaks we make, as soon as we get the answer, we can export all of this out to CAD, out to GIS, for someone to incorporate into a plan set. So we're going to push out all the 3D information, all the top, bottom elevations, the pipe network, all the slopes. So that's really when we get to that submission and reporting part. Everything in XPDRAINAGE, just push it on out, and it'll be the layout in plan, and we're going to also have all the kind of the 3D-ness that people need, and it's quite laborious to kind of manually make up in CAD. So I could clearly talk about hydraulics and hydrology all day. That's really what I wanted to touch on in this webinar. So there are actually some great questions coming in, and let me try to get some of these ones that aren't already answered. So I guess the first one that I just saw, so again, really, this is a great question. I'll just read it verbatim. The main issue I'm facing is providing to municipalities that the pipes are dimensioned correctly using dynamic calculations. This is kind of a classic, something I personally have run into. I guess maybe that's why I jump on this one first. So that's a real thing. So even if, let's say, you're using a full hydraulic analysis tool, right? There might be someone, I'm just going to say, at a county, maybe there's someone that wants to review it a certain way, or their standard is to size a pipe network with the rational method, right? They might say you need to do a full hydraulic analysis to ensure that the 100-year rainfall event really doesn't impact negatively anything off-site. But specifically for pipes, they need to be sized or assessed with that, what I'm calling preliminary sizing. Well, you can absolutely do that in XPDRAINAGE. And one thing that I personally have done in the past is this is really an opportunity, I guess, with XPDRAINAGE as a tool, an opportunity to meet the local criteria, right? But then also counter that. So, hey, here is a preliminary sizing pipe network. And again, I say preliminary sizing, that's what the Federal Highway Manual calls that approach, preliminary sizing. So I use the rational method, Manning's equation, here are the size of pipes I need. Well, in many cases, even if you only have a 5-year, rainfall event, that might be so conservatively large that the 100-year flow will fit in the pipe network. So perhaps if you're trying to save your client a lot of money, that's probably the first one that comes to mind for me. You could say, hey, review authority, hey, county, let's say that I'm in. Here is what the pipe network would be. You're saying I need to protect it against the 5-year event. Well, here's the 5-year event with the rational method, and great, here's the answer. But you'll see if we have more of a realistic, dynamic computation, we'll see that the pipe network can be a lot smaller, and we still aren't having any flooding. We're still containing the 5, maybe 10-year events in the pipe network. So this is really a way to, it's a way to communicate, right? So you can show them, all right, here's your preliminary rational approach, but can we use this, and here's why. So that's often how I've seen a lot of people, beyond myself, it's an open dialogue, right, when you're submitting a project or working on it. So, hey, this full analysis, probably a more realistic answer, and it's going to save everyone money. So, hey, can we just use this? So again, having it all in one place in XPDRAINAGE kind of lets you have that conversation, as opposed to what I used to do is, have a bunch of different spreadsheets and have a couple different hydrology tools and piece it all together, okay? So thanks for that. There's a couple questions about the XPDRAINAGE and the simulations. I'll try to talk to these. So one is it correct to say, yes, XPDRAINAGE, does it do the dynamic calculations and the pipe sizing? Specifically hitting the apply these sizing criteria, that's just for preliminary sizing, right? So I showed in the software, okay, what size of pipe is needed based on minimum velocity, let's say. That approach, that is a preliminary sizing approach, and that's done with the rational method as inflow. The dynamic, the full hydrograph system is well, that's performed using a full hydrograph approach. So it's kind of, well, do you want to set out certain sizing criteria to start with, or do you already have a kind of a starting pipe size, and do you just want to run that through your hydraulic dynamic assessment? And just to be pragmatic, right? Just what's the flattest pipe in the network? Does that work? Well, then you're probably good. Again, everyone does things differently. So there's a number of ways to approach this, and you have all the options here in one place. Okay, so you can jump around, and as I showed in the PowerPoint slides, you can look at steps 1 and 2 and then go dynamic, however you want to bounce around. Okay, so a couple questions on like regionally specific items. And again, my name, I'll go to my next slide here. Hey, my name is Zach. This is what I do all day long. I talk about this kind of stuff. So I am more than happy to talk about regionally specific design criteria, how to approach it for different areas. There's a question about Florida, and I have experience in Florida. I've worked with consultants a lot more than I've really worked in Florida, but I can talk about maybe how to approach that area. Another person mentioned working in the UK and Ireland. That's actually for Europe and the UK specifically. Yes, we actually have the RefH method and the rainfall that is needed in the UK, as well as design criteria and whatnot. So this is a tool that is used actually in the UK as well. But certainly for diving deep, this is a big public webinar. Hey, you have specific questions. I am more than happy to chat and to figure out, get my head around kind of what you're doing and what you're required to do in your area, and we can kind of talk from there. So there's a couple questions here about I guess different types of analysis. There's a comment of, what's the difference between 2D and 3D hydraulic analysis? And so I guess I'll talk to that specifically. So 2-dimensional analysis and 3-dimensional analysis. I don't know, I guess the more the more in depth you get, the more it becomes academic, okay? 3D assessment isn't something I guess most people do. I guess think of like a harbor design. I don't know, you want to have the bathymetry and how sediment accumulates around piers. That's the only time I've personally seen 3D analysis used. 2D analysis is for really broad floodplain analysis, stuff like that. Again, flooding or real coastal design. So thanks for joining. It looks like that's really kind of, I think we've covered all the questions one way or another here. If I didn't get to something, if I just skipped over it visually and didn't see your question, yeah, please contact me. I'm happy to talk. Thank you all for joining, and it's my pleasure. So everyone have a good day. Thank you very much.